Hello. In this video, in the case of atomic and molecular spectra, we are going to discuss about space quantization. Now, when an atom is placed in an external magnetic field, the electron orbit precesses about the field direction, which is the Larmor precession that we have discussed already. Now, the electron orbital angular momentum vector, that is the L vector, that traces a conic section or a conic path about the magnetic field such that the angle theta, that is between the orbital angular momentum and the external magnetic field, that always remains constant. So if we are to consider that, once again I can probably try it for you. This is the external magnetic field that is acting along the z-axis, and we have the precession of the electron about that. Now the angular momentum that remains at a certain angle with respect to this this vector. This is the b vector, which is acting along the z-axis, and this is the angular momentum that is acting at a constant angle theta. It is making a constant angle theta with respect to that magnetic field, such that the z component of the angular momentum that always lies along the external magnetic field, and the electron somewhat will be moving along this direction supposedly. So this has all been discussed in the previous video. This is the orbit of the electron, and the electron orbits and the angular momentum makes a constant angle theta. Now, with all of this, what we are going to discuss in this video is that the space, the allowed space for this angular momentum to act. We are going to discuss about the allowed space over there. Now we know that the electron can stay at any point. There's a probability of it staying in any point whatsoever within that atomic structure. This is as per the discussion that we have been having on this topic. But we also know that there are places where the probability is pretty high. That is, the places to find the electron is much higher. In case of, suppose we say the s shell, in the s orbit we say that it is spherically symmetric, so that means the probability of finding the electron is in that spherical symmetric cloud or space. Now, with that magnetic field that is acting along the z-axis, we have the component of the orbital angular momentum. So we have Lz, that is the component along the z-axis, to be having the value L cosine theta. So which means that cosine theta is simply Lz over L. Now quantum mechanically, the magnitude of the angular momentum L and its component Lz are quantized, and they are quantized as per the relation, that is L is equal to L times of L plus 1 all under root h over 2 pi, or h barred, and then we have Lz to be equal to ml h over 2 pi, or h barred. So these values, you know them, that is L and ml. L and ml are the orbital and magnetic quantum numbers respectively. Now the angle theta, that is between L and the z-axis, that is determined by the quantum numbers L and ml. They are determined as per the relation that we have given over here, that is cosine theta is equal to Lz over L, and if we put these values over there, then we get the value to be equal to ml over L times of L plus 1 under root, and that is exactly the angle that it will take, or it will take up these angles and it will stay in its place. Now since for a given L there are 2L plus 1 possible values, so for a given L we have 2L plus 1 possible values, and that is values of ml, which is varying from right from 0, then again plus minus 1, plus minus 2, and it carries on right up to plus minus of L. So these are the values of ml that it will take up, and the angle theta can therefore assume 2L plus 1 discrete values. In other words, the angular momentum vector, that is L vector, can have 2L plus 1 discrete orientations, because that orientation means the theta will depend on those values, those different values. So 2L plus 1 discrete orientations with respect to the magnetic field. Let's take up a simple one, and we'll see how it is quantized. Let's take up, let's say for L is equal to uh, 2, we have the value of L to be equal to root 6, that is 2 into 2 plus 1, that is 3. So 2 times of 3, that is 6 under root h bar, or h over 2 pi. And for L is equal to 2, we'll have the values of ml to be varying from 2, 1, 0, minus 1, minus 2, 5 values of that. And as a result of that, we have Lz to be having the values 2 times of h bar, and then we have simply h bar, and then 0, minus h bar, and then minus 2 h bar. So these are the values of Lz. Now the orientations, that is theta, for L with respect to B, that is the z axis over here, can therefore be calculated from these values. That is, cosine theta will be equal to ml divided by L times of L plus 1 under root, and that will give us 2 over root 6 for the first value. Then we have 1 over root 6, the third one being 0, the next one being minus 1 over root 6, and the last one is a minus 2 over root 6. So these are the values that it will take up, and from that we can obtain the value of theta. So the value of theta in these cases will be the cosine inverse of that. That will roughly be equal to 35 degrees for the first one, 66 degrees for the next, 90 degrees when theta is cosine theta is 0, and then 114 degree, and then finally 145 degree. This is the other way around, because 35 degrees, 180 minus 35 is 145 over here. So 35, 45, correspondingly 66 and 114. So this figure will give us an idea about the space quantization. The space is quantized therefore, because we only have allowed values of these of the angular orbital angular momentum, and as we can see, for various values of theta, we have different orientations of the orbital angular momentum, that is L. So first one is given with respect to the z-axis, that is the direction of the external field, as well as the Lz component acting along that direction in the upward direction. With respect to that, the L vector has an angle 35 degrees, then 66 degrees, then 90 degrees, and if we further extend it, then we'll find that this is right up to this one is going to be 114, and the last one is going to be more than that, that is 145 over here. The last one, you need not draw it, it will get clumsy. So this total angle, the orientations of the angular momentum, tells us that the space is quantized in that case. Finally, it also tells us that the angular momentum that cannot be aligned exactly parallel or anti-parallel to the B vector, because in that case we'll have ml to be equal to the value of root over of L times of L plus 1. ml has to be less than the value of root over of L times of L plus 1, because that is the value for the capital L, and Lz is its component along the direction of B. so the component will always have lesser value with respect to the original vector, the L vector, that is. Then next we take up the case of electron spin. Now Bohr-Sommerfeld quantum theory of the elliptic orbits with relativity correction, that was in numerical agreement fairly with the observed fine structure of hydrogen spectral lines. However, as we know, it suffered two major drawbacks. The first one being that the Sommerfeld relativistic explanation could not be applied for the spectral lines of atom other than hydrogen. For example, the spectral lines of alkali atoms are doublets having two close fine structure components. In alkali atoms, the optical electron moves in a Bohr-like orbit of large radius at low velocity. Therefore, the relativity effect would be too small to be taken into account, and therefore fine structure splitting of the observed alkali lines, it cannot be explained. Secondly, the simple quantum theory, it failed to explain the anomalous Zeeman effect, that is, the splitting of the atomic spectral lines into 4, 6 or even more components when the light source was placed in an external magnetic field. So in an effort to remove these two drawbacks of the theory, Goudsmit and Uhlenbeck, let me write their name, they must be credited with it. So Goudsmit and Uhlenbeck, they proposed in the year 1925, they proposed uh, a theory that the electron must be looked up as a charged sphere which is spinning about its own axis, having an intrinsic built-in angular momentum and consequently an intrinsic magnetic dipole moment as well. Therefore, it will have a angular momentum which is known as a spin angular momentum. So it was attributed with an angular momentum, that is the spin angular momentum, just like the orbital angular momentum of the orbit of the electron. And then also we had the spin magnetic dipole moment. We take it as mu s, spin magnetic dipole moment. It will behave as a dipole obviously, because a charge moving along a circle, it will behave as a dipole, so it will have a spin magnetic dipole moment as well. Now these were the additional stuff which were added to the orbital angular momentum as well as the orbital magnetic dipole moment mu L taken previously. Now if we take up the language of how the orbital angular momentum and the dipole moments were dealt with, we'll have the value of the spin angular momentum s to be equal to root over of s times of s plus 1 h bar. Now here the only value that we can use for the s, that is the spin quantum number, so this is the spin quantum number, we can only use two values, that is half and minus half. It can take up only two values, and if we are to use that plus half over here, so we'll get s to be equal to half plus 1, and that gives us that multiplied to h bar obviously, that gives us root 3 over 2 h bar. And as far as the component of the spin angular momentum is concerned, we have sz to be equal to ms times of h bar. Now ms again takes up two values, that is half and minus half. So if we have ms to be equal to plus half, then we have, so ms takes of plus half and minus half as the values, and if we are using plus half, then we have sz to be equal to half h bar, and we have also sz to be equal to minus half h bar when ms takes the negative value. And it has been concluded from experimental data that the gyromagnetic ratio for electron spin, that is mu s over s. Now we had the value mu l over l, so now we have mu s over s. Now mu l over l, if you remember, the gyromagnetic ratio was E over 2m. This is something different. We have the gyromagnetic ratio for this to be equal to uh, twice of E over 2m. So that means we have mu s over s to be equal to minus of 2 E over 2m. Minus of 2, the minus sign indicates that it is acting opposite, that is mu s is acting opposite to the direction of s, that is the spin angular momentum, and then uh, mu s is acting opposite to that. That is what I'm trying to say. And the factor 2 has come up in this case, as opposed to the case of the orbital angular momentum with respect to the orbital dipole moment. Now if you will recollect, we had a g factor associated with the angular momentum and orbital the orbital angular momentum and the dipole moment. Here also we have the g factor, but there the value of the g factor was 1, while in this case, if we use these values, that is mu s is equal to minus of gs times of E over 2m times of the s vector. The s vector has been cross multiplied in that case. So here the value of gs, as you know, will be equal to 2. This is the spin g factor. We can express the spin magnetic dipole moment in terms of the Bohr magneton as well. So we can use this relation. So we have minus of gs, mu b is the Bohr magneton. In that case we divide an h bar and we have the s. We divide h bar because we have multiplied that as well to obtain the expression for the Bohr magneton mu b that we have used over there. And the possible components of mu s along the z-axis, they can be given as possible components of mu s along the z-axis. They are given by mu sz, that is equal to minus of gs mu b over h bar, and then we have sz, and that is simply equal to minus of gs mu b, as a Bohr magneton, over h bar, and we have the value of sz to be equal to ms times of h bar. So the h bar terms get cancelled out, and we have minus of gs mu b times of ms. Now because g is 2 and we have the value of ms to be equal to either plus or minus 1, so we have this from this expression. You can also write mu sz to be equal to plus or minus of mu b. So this is how it is related to the Bohr magneton. The spinning electron, the concept that proved to be successful in explaining not only the fine structure and the anomalous-Zeeman effect, but other atomic effects also that we will be observing later on in our discussions. Although the electron spin was introduced as a postulate, but in 1928 Pam Dirac proved on the basis of relativistic quantum mechanics that an electron must have an intrinsic angular momentum and an intrinsic magnetic moment, which were just the same as attributed by Gaudsmit and Uhlenbeck. Thus, the electron spin was put on a firm theoretical foundation. The practical evidence of its existence came from the Stern-Gerlach experiment that we'll be dealing with later on in our discussion in this topic. So that's all from this video on the case of space quantization and the electron spin. We'll be discussing more about this in the next video. Till then, thank you for watching.